Welcome back. We are going to start with the last lecture. We saw what the Shazy equation and the Shazy coefficient was, and now we are going to start with the Manning's equation. We found out that Shazy related the velocity proportional to RH to the power half, where RH is A by P, area divided by wetted parameter, and RH to the power half was what Shazy derived. However, through a series of experiment, a scientist called Manning found out that the dependence of the velocity on the hydraulic radius is not to the power 0.5, but V was proportional to RH to the power 2 by 3. He therefore proposed a modified equation for open channel flow, where he said that V is proportional to 1 by n A to the power half RH to the power 2 by 3, and this is equation number 18, and this equation is called the Manning's equation, and parameter n is called Manning's resistance parameter. Okay. N is generally obtained from the table, which I will show you. The precise value of it is very difficult to obtain. So, we generally use tables for finding those values of n. In your case, those values of n will be very standard or will be given to you at the time of the questions. So, an important thing to note is the rougher the parameter is, the larger the value of n will be. Okay. So, I will just go to the Shazy's so there is a correction here actually. So, this is not A, that is S naught to the power half. Okay. So, I will rewrite is, sorry for the okay. So, what Shazy proposed was this. Okay. All right, same as what I had written before. All right. So, Manning's n table. So, this is the general value of the table. Okay. So, if the wetted parameters, if the natural channel is there for a different type, for clean and straight channels n is 0.030, for sluggish with deep pool it is 0.040, for most of the rivers it is 0.035. So, as you see, for different natural channels, for flood plains, for excavated earth channel, and n has been found out. Okay. For artificially lined channels as well, you can actually control the roughness and prepare for glass. If you see, n is very less, 0.010, brass is 0.011. So, if there is a casted iron, if there is a wood, for the clay tile it is 0.014, for brickwork. So, what normally you do is, you look at these tables and find out the value of n. Okay. Some for alpha asphalt lining is 0.016. You do not need to remember those values, but you should have an idea. For example, natural channels is around 0.035, glass is around 0.010, but in majority of the problems you should be given, if you are not asked to find out the roughness, you should be given what the Manning's parameter n is inside the question itself. So, we start by doing a class question. The question is, the water flows in a canal of trapezoidal cross section which is shown in figure below. Let me see where the figure is. We have to find the area A, wetted parameter, flow rate and Froude's number for this case. You see, the channel is given here, and this is trapezoidal cross section, okay. And it says that the bottom drops 0.42 meter per 304 meter of length, and the canal is lined with the new smooth concrete. So, it is written new smooth concrete. So, we can look up the value of n, and after looking the value of n, we know that it is 0.012. That is already given to us, and following are the things. This is a very classical example where you will learn how to do this type of problems. Area we will find out, we will find out the wetted parameters, we will find out the flow rate, Reynolds number, and in the end the Froude number as well. Okay. So, this you see it is given in feet, correct. So, 5 feet and 12 feet. This problem has also been taken from Munson, Oki, Shenyang. This gives a very clear cut idea how to, one of the most simple cases of finding uniform flow, hydraulic radius and the flow rate and everything. So, okay. So, we start. So, this is the figure. So, area is going to be 3.6 into 1.5. So, this is this area, correct. Because we have converted it already into meter square, okay, plus this is half base into height, correct, and half base into height. So, when you add this, this will become 1 into base into height. Base is half. So, height is height is half and base is so it becomes 1.5 divided by tan 40, and this will come out to be 8.08 meter square. All right. So, now we need to calculate parameter as well. The parameter that is wetted is going to be this length plus this length plus this length, because this is the length which is wet, correct. So, we can find this plus 2 times this, because this is equal to this, all right. So, perimeter, this one is 3.6 in meters plus 2 into one of these length. This is going to be 1.5 divided by sin 40. Okay. So, this is 1.5 to sin divided by sin 40 will give us 8.26 meters. So, we have calculated the first 2 parts that we needed. Area is coming out to be 8.08 meter square and wetted parameter P is coming out to be 8.26 meters. So, hydraulic radius is going to be A by P, and 8.08 divided by meter square, almost 0.99 meter, almost. Okay. So, R is coming out to be 0.99 meters. Okay. So, because it is the radius, it is the dimension of length. So, it is in meters. All right. We have also been told that the bottom drops 0.42 meters per 304 meter. Therefore, we have been indirectly given the slope S naught. It drops 0.42 meter in 304 meters. So, S naught, that comes out to be 0.0014. You see, we have already told you many times that S naught is very small. So, here in the practical problem also we find S naught is very small. It is the order of 0.00. So, 0014 to be specific. We will see in the next slide. Okay. So, S naught is 0.42 divided by 304. Now, how to find the Q? So, we know V is 1 by N, right, RH to the power 2 by 3 into S naught to the power half, implies Q is V into area, correct. So, area into 1 by N RH to the power 2 by 3 S naught to the power half. N we already know, N was, for finished concrete N was 0.012, that we already looked up from the table. Area we have already calculated, 8.08 meter square. RH also we calculated, RH was 0.99, and S naught also we calculated was 0.0014. Okay. So, if we substitute in these values, we are going to get 0.30 by N. Now, N we have not yet substituted, but N for finished concrete is 0.012. So, the Q comes out to be 25 meter cubes per second approximately. So, we have calculated, we have used the Manning's equation and calculated area, we have calculated parameter, we have calculated the discharge Q for this channel for a uniform flow condition. Alright. So, the next question says we have to calculate the Reynolds number. So, Reynolds number is given by Reynolds number H V by nu, and this is the hydraulic radius. So, this is the characteristic length, as I told you in the beginning. It mostly it is the height, but in open channel flow it is hydraulic radius, not RE, it is R, RH into V by nu. Okay. So, R we have calculated, V we know already, alright. So, V is Q by area, correct, and nu is fixed quantity for water. So, RE is RH V by nu. This is an important formula that you must remember. For open channel flow, this is the Reynolds number, this is the Reynolds number, and if we calculate, we substitute in the values. RH is 0.99, V is Q by A, and nu is 0.13 into 10 to the power minus 5. Alright, and on calculation it gives 2.3 into 10 to the power 6. So, this is turbulent flow. Okay. As we have all, as this we have discussed this, that most of the flows in principle in open channel flow will be turbulent. Froude number is V by under root GH or GY, Y is the depth, correct. So, V we already know, we have calculated 25 by 8.8 is 3.1 under root 9.8 into Y is the water depth. So, 5 feet comes out to be 1.5 meter, and this comes out to be 0.808. So, it will be a subcritical flow. Anyways, so I have put it also in the slides. So, it is 3.1 divided by 9.8 into 1.5, that is 0.808. Okay. So, you see, we have found out all the questions, all the things that we wanted to. So, we go to solve another question now. It says that water flows in a channel shown in figure below. This is the figure at a rate q is equal to so water flows along a drainage channel having the properties shown in this figure. Okay. If the bottom slope S naught is equal to 0.3, so we have already been given S naught, estimate the flow rate when depth is y naught, depth is 0.24 plus 0.18, that is 0.42. Okay. So, we have to take 1 feet is equal to 0.3 meter, the whole configuration is given actually. So, how do we solve this? We also have to obtain an effective Manning parameter. See, because this channel is composed of 3 effective, different N1s, you see. So, in this part the Manning's roughness is 0.20, in this one it is 0.015, so N3 0.030. So, we have to find an effective Manning parameter, N effective. All right. So, how do we solve this problem? We will go step by step. So, first we redraw the diagram here and we divide the cross section into 3 subsections, and the total discharge is going to be Q1 plus Q2. This is section 1, here it will be Q1, it will be Q2 and it will be Q3. So, we find separately. So, now for each cross section Qi is going to be, we use the Manning's formula, A1 into RH to the power 2 by 3 into S naught and Ni. S naught is common for all, okay, that we have seen. S naught was given here 0.002. All right. So, we find Q1, Q2 and Q3. So, best is that we do one simple calculation of A and P. Let us say we do it for cross section number 2. So, we are going to see this calculation. So, area A2 is going to be this is the width 0.6 into the total height is 0.24 plus 0.18. So, area is going to be 0.6 multiplied by 0.42 is 0.25 meter square A2. Similarly, the wetted parameter is going to be only this one plus this one plus this one, all right. So, this is 0.6 meter or 2 feet and this one is 0.8, and if you multiply it with 0.3 it will be 0.24, and we have 2 of those, 1 and 2. So, 2 into 0.24 and this gives us 1.08 meter. All right. So, A2 was 0.26 meter square and this was 1.09. So, hydraulic radius is going to be 0.26 divided by 1.09, it comes out to be 0.238 meter. All right. So, now if we list each of them, we did the calculation for number 2, you should be able to do the calculation for section number 1 and 3, all right. So, we find out A1, P1, hydraulic radius and N1 is given. So, similarly, in all the 3 ways you can list all 3 of them in this table and the value has been written, okay. You verify it after the lecture. So, the total flow rate is Q1 plus Q2 plus Q3. So, with those values, area multiplied by RH to the power 2 by 3 and this is S naught, okay, because see what the formula says, divided by 1 by n. So, this is N, Manning's N, which are different for different. This is S naught, this is areas AI, NI, and this is RHI. Okay, and you sum it, and you will find out that Q is equal to 0.46 meter cube per second. So, if now we have found out everything for entire, we have found out Q. Now, if we assume that if entire cross section were considered as one flow area, then the total area is going to be A1 plus A2 plus A3, which we have already computed in the tables. If you add it, it will come to be 0.59 meter square. Okay. The whole parameter, if you count P1 plus P2 plus P3, it is going to come to 3.27 meter from the table. You find it from table, and same is from the table, and add, and you get these values, the table that we have written. All right. So, effective hydraulic radius is A by P, and it comes out to be 0.180 meter. Okay. Now, Q can be written as A RH to the power 2 by 3 S naught to the power half divided by N effective. So, this is the effective Q, which we have already calculated, Q total, right. Area total, which we have already calculated, P we have already, we know. So, RH, sorry, so this RH will be this one here, S naught is constant, same for all, correct. So, N effective is going to be A RH to the power 2 by 3 into S naught to the power half divided by Q. So, A is 0.59 into 0.81 to the power 2 by 3 into 0.002 to the power half divided by 0.46. So, N effective came out to be 0.0179. Okay. So, this lies between N2 and N1 and N3. So, this question we have solved. So, what we did, we had a complex cross section. In that complex cross section, there were three parts, part 1, part 2 and part 3. So, for each part we found out areas AI, right. We found out parameter I, we found out hydraulic radius RHI, we found out QI, all right, and then we summed all the discharges to find the total Q in that section. Okay. Good. With this, we will move on to the next question that will give us more practice. So, the question is that the water flows in a channel as shown in this figure below. At the rate Q is given here 10 meter cube per second. It says the canal lining is VD and its Manning's roughness is given. As I said that most of the time it will be provided to you. And now the question is determine the depth of the flow. It is a very simple to calculate. You see, it is again given in terms of feet. The reason is that most of the irrigation thing earlier was in this feet system squared. So, generally the question, but we use the conversion system actually. Okay. And we are going to solve this. So, the cross section is given, we will be able to find out the area, and if we assume, actually we have to find this y, all right, which actually is given here, the solution is given, but with these values Q is equal to 10 meters cube per second and N is equal to 0.030, these length is given 12 feet. We have to calculate the y. So, how to attack this problem? Very simple to do. So, in this instance neither the flow area nor the hydraulic radius is known, although they can be written in terms of depth y. Hence, in terms of meter, this is actually the bottom width is 3.66 meters, okay, and the area can be written as 3.66 into y plus half into half base into height plus half base into height. These are symmetric, so we can write half plus half 1. So, y into y by tan 40, correct. This one is y by tan 40 because angle is given to us. So, in terms of y we are writing, this will come, area is going to come as 1.19 y square divided by 3.66 y, where a and y are in square meters and meters respectively. All right. We have assumed it in terms of meters. The perimeter, so this length is already known, 3.66, correct, plus 2 multiplied by, because this is 1 and plus 1. So, this will be, if this is y, this is going to be y by sin 40, fine, and this is what we have done. In terms of y, we have also written the parameter 3.11 y plus 3.66. So, the hydraulic radius will come area by perimeter, that is 1.19 y square plus 3.66 y divided by the perimeter. Okay. The discharge according to the Mannings is given by 1 by n is given as 0.03. Area we have written in terms of in the previous slide we have found out, this is RH to the power 2 by 3, this is RH, and S naught is given as well, 0.0014 to us. Okay. All right. Now, if we, and what is the value of Q that we are going to use, that is Q is 10. It is a complex calculation, but if you solve using this, you will get an equation like this. All right. So, you can use mathematical techniques. This is not a question that will be given to you in exam or test, but this is just to demonstrate how things can be found out. Okay. So, the solution of equation can be obtained easily by use of simple root finding numerical technique or by trial error methods. The only physical meaning roots of equation 1 give the solution for the normal flow depth as this flow rate as. So, this will satisfy, and the techniques is trial and error, for example, fine. And this type of questions where trial and error, it will not be given in your test for this particular course, but it's, as I said, it is important, so that you should be aware of these type of questions. If the calculation is simple, definitely it can be given, but here the calculations in the end become so complex, you are unable to solve it using the calculator. Okay. So, this is the final value of the normal depth. All right. So, I will close this lecture here, and we will resume with the next questions and topics in the next lecture. Thank you so much.